Hello, you tens. Welcome to a new video on sketching quadratics. This time we're going to learn how to sketch quadratics using completing the square. So, a few things to notice here. First of all, if we're asked to sketch these two quadratics, our normal approach would be find the x-intercepts, find the y-intercept, find the turning point, draw a line through them all. So very quickly with this one, we would let y equals 0 for the x-axis to intercept, so 0 equals x squared plus 5x take 6. X take 3, x take 1, x plus 6 multiplies and adds, fine, so the two x-axis intercepts are 1 and minus 6. We would then let x equal 0 to find the y-intercept, so the y-intercept would equal minus 6 also. We could then find the turning point, etc. That all works beautifully. Of course, what it relies on is us being able to factorize and find x-intercepts. If you can't factorize and can't find x-intercepts, then where do you know it crosses the x-axis? And how do you draw it if it doesn't cross the x-axis? So for example, take this one here. We know that it crosses the y-axis, so its y-intercept is positive 2. That's easy. But if you tried to factorize it, you'd find you couldn't. And this presents us with a problem, because how do we know where it's turning and getting through the y-axis? We know it's crossing at 2, but is it doing that? Is it doing that? Is it doing that? Is it doing that? There's lots of different ways a quadratic can go through the point y-axis equals 2. So today we're looking at graphing where we can't factorize to find the x-intercepts. And to do this, we use something called turning point form. And you'll have seen it at some point last year also. Turning point form looks like this. A bracket x take h squared plus k. Now, to look at this more closely, we can look at it on, that's not it, Desmos and Desmos. So here, what I've set up is a quadratic. I hope you can see my cursor in the top left, of the form a x take h squared plus k. And right now, k, h, and a are all set to 0. So really, the quadratic that we're looking at is, if I can blow that up just a little. Oh, struggling, that'll do. Currently, we're looking at the quadratic y equals x squared. All of those set to 0 just leaves us with x squared. If a is 1, a is 1, k and h is 0. Alright, let's see what happens if we adjust h a little bit. If we increase h to 4, it translates the graph horizontally in a positive direction. So the graph we're now looking at is this one here. Y equals x take 4 squared. Note how it's negative 4, and really h over here has become positive 4 because that negative is set into the equation. Easiest way to think about it, and you will have seen this in year 9, is this number, this here, is the opposite direction to which you'd expect. If it's x take 4, the graph has translated 4 in the positive direction. I'll show you what I mean. If that's jumped back to minus 3, pretend it's minus 3, I can't hit it on minus 3, then when the graph we're looking at is the graph y equals x plus 3 squared. And that's done a horizontal translation in the negative direction. Alright, so this h term, this term inside the brackets, controls the horizontal translation. Now, let's look at the k term. So I'm just going to set that at 2. Can't even hit 2. 3.2. It doesn't matter. Let's look at k. As k increases, the graph moves up. As k decreases, the graph moves down. Essentially, a positive k represents a positive vertical translation. Negative k, negative vertical translation. The k on the end just translates the entire graph up or down. Now, what does the a do? Well, we looked at the a quite a lot in year 9, but if a is 1, then it's a normal convex quadratic. If a is greater than 1, it's still positive, convex, but narrows. If it's between 1 and 0, as long as it's positive, it stays convex, it just broadens out. At 0, we have a straight line at the line y equals k, and as we drop down into the negatives, the exact same thing happens as with the positives, but it's mirrored on the y-axis. So it now just becomes negative and steep, concave and steep, or between -1 and 0, broader and concave. Now, I've spoken for quite a while already, and this video will go for a while, so if you feel like taking a break, you can do that in 1 second. First, we want to say that A affects concavity, so it's concave, convex, it does that, or that, and width. So whether it's that, narrow, wide. H, horizontal translation. K is vertical translation. Now this is called turning point form, because taken like this, our turning point from that equation will be equal to the point HK. So as we saw in Desmos, H and K now determine the turning point. If H is 3.2 and K is 1, then the turning point will be 3.21. If it is minus 5.31, then A minus 5.31. A doesn't affect the turning point, it just flips around on the same turning point. Another way of thinking about this is if you have an equation that looks like this, say y equals x plus 2 squared take 4. Well, we know that the turning point is going to be -2 minus 4. And because it is a positive one out the front, we know it'll be looking like that. So we're looking at a minimum. How do we remember that is -2 when there's a positive 2 staring at us there? We can try and think about, well, how do you make a minimum from this graph? At what values are going to create a minimum? Now, anything squared is going to be positive. All right? So we want to minimize that positive number to make this a minimum. So we know that that term in here minimizes at the point x equals -2. Because -2 plus 2 is 0, 0 squared is nothing. So at the lowest point, it is going to be at -4, so that's taking down to the lowest point when x is -2. When x is not -2, for example, if x was 1, or if x was even -1, -1 plus 2 is +1, +1 squared is 1, 1 minus 4 is -3, which is higher than -4. So that indicates how we're getting to our negative, how we're getting to our turning point, and what level the turning point's at. So we're getting to the turning point at x equals -2, and the y level of the turning point at that point is -4. I feel I'm rambling. So I'll show you how to actually sketch the quadratics using turning point form. Taking the same example we had above, you may notice that turning point form looks suspiciously like what happens after you complete the square. Good news for us is that any quadratic, say this one, can be converted into turning point form using completing the square. Bad news is we're using completing the square and it's going to get ugly occasionally. However, for purposes of simplicity, I've chosen a relatively nice one. So let's complete the square. Completing the square, we know we take b out, write it over 2, square it, 1. Lovely. And then we have y equals x squared plus 2x plus 1 plus 2 take 1. Note that we're all doing it on one side of the equation. I realize some of you got used to doing it the other way, but please do it this way because it doesn't make much sense to add 1 over there with y. Now, that's equal to x plus 1 squared plus 1. That was an easy one. So our turning point is the point -1, 1. -1, 1. I know I'm turning there. But am I turning up or down? Well, we need to find the y-intercept. So we let x equal 0, and therefore we have y equals 0 plus 1 squared plus 1, which is just going to be 2. So therefore we are turning at the point minus 1, 1, and crossing it 2. And that gives you enough for a graph. Now my graph isn't very accurate. I'll see if I can do a better one. And the way you can do a better one is note how this here is 1 across, 1 up from the turning point. It means if you go 1 across, 1 up, there'll be an equal point there. So it's symmetrical around that turning point. And if you know the y-intercept, you also know another point on the graph over the other side. So a better quadratic graph would be like that. Of course, without all these messy bits here. Pretty happy with that one. Alright. Please sketch the following quadratic using completing the square. And remember, for completing the square, your leading coefficient must be 1, so deal with the 4. But don't forget about the 4, because it affects your y-intercept. Alright, thank you very much. I'll see you next lesson.